Hello, friends. Welcome back to You Can Do TV. You don't install a 250-ton machine inside a building. You build the building around it. The parts it cuts are bigger than most houses. The acceptable error is a hair across 6 meters. Get any stage wrong. Sand, mold, melt, machining. And the casting fails late and expensive. Walking through every step and closing with one final layer underneath it. Before we explain what this machine makes, take a second to process what this machine is. The Titan SKDW 160/130 is not workshop equipment. It is a 250-ton vertical turning lathe with a 15,000 millimeter table, able to carry 1,100 tons. It arrived across 72 trucks and 35 oversized loads, with 300 kilometers of cable and 18 CNC axes inside. At this scale, precision manufacturing becomes architecture. The machine does not simply get installed inside a building. The building gets built around it, around steel, motors, and gravity massively. If the VTL is the king, the heavy lathe turns the kingdom's shafts. A pickup-length workpiece spins while a cutting tool peels metal away. A technician standing on the bed proves the scale. This is a lathe large enough to make a car look small. Now double cutting heads, and the production math changes completely, which raises the obvious next question. What exactly are these enormous machines cutting, and why does it need to be this big in the first place? Here's the twist most people never see coming. The massive parts those giant machines cut didn't start as solid blocks of metal. They started as sand. In a 433,000 square foot foundry, gray and ductile iron castings serve construction, agriculture, mining, and energy. Patterns are barcode scanned, molds move fast, and magnesium changes brittle gray iron into ductile iron, metal that bends before it breaks under punishing industrial force. Scale up to 100,000 tons of production capacity per year, and the numbers stop feeling like numbers. Automatic green sand lines, core rooms, a 138,000 volt substation, and 25 MVA of dedicated power exist because melting metal is controlled energy on an extreme scale. After cooling, gates and risers are removed, surfaces are shot blasted and deburred, and parts may be machined or pre-assembled before leaving the facility. The reason all of this infrastructure exists is simple. You cannot machine a hollow, complex internal geometry from solid steel. You have to cast it correctly, repeatedly, and at industrial scale safely. Want proof that solid machining has hard limits? Try making a 64-inch diameter pipe from a solid block of steel. You would need truck-sized stock, waste most of it as chips, and spend impossible time. In Birmingham, recycled scrap melts in a 70-foot cupola, flows into a 50-ton ladle, receives magnesium, then spins inside a centrifugal caster. Rotation spreads ductile iron evenly against the mold wall, producing pipe from 4 to 64 inches for century-long water service. Casting here isn't the cheaper option. It's the only option when geometry, volume, and economics collide reliably, repeatedly. Now apply that logic to mining, where the parts have to survive things no pipe ever faces. A Duluth foundry pours mill liners, crusher liners, grinding media, and specialty castings for 6 continents. Inside crushers and ball mills, impact, abrasion, and chemistry attack nonstop. Custom alloys matched to ore and machine geometry can turn weeks of wear life into months, and months of uptime into millions of dollars in recovered production. Here's what a modern foundry that supplies precision castings internationally actually looks like. And it starts nowhere near a furnace. Engineers begin with drawings, 3D models, and magma simulations that predict flow, shrinkage, hot spots, and stress before sand is mixed. If the simulation is wrong, days of tooling and tons of metal can be lost before anyone sees the defect. CNC machined wood or composite patterns define the geometry every casting inherits. Induction furnaces hold metal near 1,565 degrees Celsius, while spectrometers verify chemistry before pouring. After solidification come heat treatment, quenching, tensile testing, ultrasonic inspection, and liquid penetrant testing to find cracks or internal defects. Finished castings move to CNC machining, final QC, certification, and international shipment for load-bearing equipment. Every step you just heard is necessary. Skip one and the chain breaks. And the question becomes, at which stage do we find out again? The answer to where quality control starts is almost always earlier than people think. And in casting, it starts with the mold, not the metal. Floor molding handles molds too large for automated lines. Steel flasks hold furan-bonded sand in shape, while patterns, gates, risers, cores, and chills are set. Refractory coating protects the mold. Then both halves are closed, clamped, and bolted before molten metal arrives for a controlled pour. Floor molding handles big, heavy, one-of-a-kind pours. But if you need tighter tolerances and a better surface finish on a smaller part, there's a completely different philosophy. And it starts with a heated metal pattern and resin-coated sand. At 175 to 370 degrees Celsius, resin bonds grains into a thin shell copying the pattern surface. Loose sand falls away. 2 shells close around a core, get poured, then break apart cleanly after solidification, leaving a sharper, cleaner casting with improved surface quality. Now here's where one foundry quietly solved a problem that the rest of the industry had accepted for decades. Complex shapes and wooden pattern casting simply don't mix. Traditional wood patterns require cores, draft angles, split lines, and cleanup fins. Full mold casting replaces them with CNC carved polystyrene foam. Molten metal vaporizes the foam and takes its exact place, often without cores. Simulation verifies the pour. Coating stops sand adhesion. Furnaces melt 25 tons in 70 minutes. Castings up to 30 tons become possible, and what they do with it next is where the real surprise comes next. Full mold casting spans dies, beds, pumps, engines, turbines, components, and ships. Finally, and then in 2013, they took it one step further and printed the mold itself. When most people hear 3D printing, they picture metal parts. Here, the smarter move is printing molds. If you want proof that foundry casting can meet extreme specifications, look at NASA. Over 100 crawler transporter track pads were cast for rocket-moving loads under forces above 18 million pounds. And now that you understand how a casting gets made, the question becomes, what happens to it the moment it comes out of the mold? Because that moment is when most castings fail. Before any of those molds can be filled, someone has to build the exact recipe of metal that goes into the furnace. And getting this wrong doesn't just ruin a casting, it ruins the entire heat. The scrapyard is organized by alloy, iron, steel, chromoly, and other grades in marked, color-coded zones. A tower engineer issues weights, while a crane operator loads a numbered bucket on an electronic scale. One wrong charge contaminates everything before melting even begins, turning precision into expensive scrap immediately before the furnace starts. The heart of a steel foundry is an electric arc furnace. And the first time you understand what it actually does, it's hard to believe this technology exists at commercial scale. 3 furnaces charge 10 to 11 tons per heat, with a maximum around 24,800 pounds and a typical cycle of 2.5 hours. The roof opens, scrap drops in, and graphite electrodes strike arcs through the metal itself. Low voltage protects the roof and walls at first. Once the electrodes bore into the charge, voltage rises, arcs lengthen, and power surges. Oxygen burners cut and combust steel, adding chemical heat. Alloys and slag materials enter mid-heat, while samples verify chemistry. When temperature and chemistry align, the furnace tilts into a preheated ladle. The department targets 85 net good tons daily and often exceeds it when sequencing works. Getting molten metal from furnace to mold without losing temperature, chemistry, or control of the ladle. That's where the next risk enters, overhead and glowing. While the furnace is running its 2.5-hour heat cycle, The mold that will receive the metal has to be ready and waiting. And the fast loop is how a foundry ensures it never runs out of molds to pour. This no-bake center averages 4 molds per hour and 40 to 48 daily. Sand mixed with furan binder hardens in about 20 minutes, then rollover equipment strips it from the pattern. Cores, refractory coating, oven drying, inspection, glue, and locators follow in tight order. The challenge is sequencing. The right mold must reach the right station when the heat taps on the pouring floor. When the ladle of steel finally meets the mold, the entire foundry schedule converges on a single moment, and that moment has a surprisingly narrow window. The pouring floor stages molds across 24 lines, with holding lines and transfer cars. Supervisors verify inventory and alloy-specific temperature. If too hot, argon cools the heat. If ready, the crane centers the ladle over the sprue. The casting is now in the mold, and the next phase is the one that actually tests whether it survives. A mold that just came off the pouring floor is running at around 1,000 degrees, and separating it from the casting it contains is not a gentle process. A vibrating table shakes hot sand through slots onto conveyors, then through a crusher, screen, bucket elevator, and magnetic separator. Clean sand drops into storage, cools through a fluidized system, and returns toward reuse silos for the next cycle. What remains is the raw casting, exposed at last for metallurgical judgment after surviving fire and vibration. Pouring metal into a mold gives you shape. Heat treatment gives you the mechanical properties that make that shape useful. Ovens transform grain structure through cooling cycles. Heat treatment set the metallurgy. Finishing is where the casting earns the right to leave the building. Riser stubs and rough faces are ground flat. Hand grinding prepares bolt holes, corners, and mating surfaces for gauges. Pins verify locations, while computerized Brunel testing records hardness against each serial number. For mill liners, hardness predicts wear life, which customers convert into operating hours before shutdown. Inspectors confirm measurements, then mark approved castings with a green dot. No dot, no shipment. A casting can look right outside and still be wrong inside until every check confirms it for service. A casting isn't a machine yet. It's just metal in roughly the right shape. The next world is heavy CNC. A gantry machining center is what you reach for when the workpiece is too big to spin under a normal mill. The frame straddles the part instead of fitting around it. Bed geometry is built so the cutter stays rigid no matter where it sits on the table. The bigger the cast, the smaller the acceptable error becomes. 1/10 of a millimeter on a 6-matra flange becomes the gap a bearing has to live with. This machining center hits 6,000 revolutions per minute on its spindle, swaps cutting heads automatically, and is built to keep geometric accuracy across the entire full travel. Add a turning table to a gantry mill, and the entire workpiece becomes a moving subject in motion. The largest check-made gantry mill of its kind runs full milling and turning operations on the same bed at once. 7 controlled axes, a 4.5 metra carousel running on hydrostatic guideways. Travel reaches 7 metras across the work area. The result? Complex 3D eccentric surfaces get cut in one setup that used to need two different machines and a careful reclamp in between. Look at one of these machines in operation, and the head-changing system is what gives the game away first. A gantry mill that can only mill is a gantry mill. A gantry mill that can swap to an angle head, a vertical head, a long reach head, and a high-speed head, all without the operator touching the spindle, is doing work that used to take 3 different machines and 2 refixtures. The mechanism is mechanically simple under the hood. The spindle drives over to a parked head, releases its current attachment into the rack, then locks onto the new one. Same spindle, different geometry, no human anywhere in the cut zone. That detail is the entire reason cycle time keeps shrinking even as the parts get bigger. Angle heads reach into pockets that would have required tipping the part on its side. High-speed heads finish surfaces the roughing head can't approach without leaving witness marks on them. The accumulated saving comes from never breaking the setup. Every refixture introduces a fresh datum error, and on parts this big, those errors stack up into outright scrap. A turbine wheel is where you find out whether the machine has the rigidity to cut, where the cutting tool has almost nothing to lean on. A table-type horizontal boring mill is the answer to that problem. The part rotates on the table. The milling head sweeps the angled fins under full multi-axis control. Travel: X 3 to 5 meters, Y 2 to 3 meters, Z 1.52 meters, W 1.25 meters. Cutting a turbine blade pack isn't one operation. It's a sequence that has to land each step in the right order. Step 1. A heavy roughing head bites bulk material off the cylindrical workpiece while it spins on its fixture, cooling spray running continuously. Step 2. The cutter switches to blade geometry milling, navigating the deep curved pockets between blades. The multi-axis setup is what makes the pocket geometry possible at all. A fixed axis mill couldn't reach in. Where the curve gets tight, the tool path slows down. Where the surface needs polish, the head switches to a finer tool. Coolant runs constant during the finishing pass. The finished turbine then spins true under its own balance, alignment proven by symmetry, not hope. A second view of the same T-class machine cutting precise rectangular pockets into a flat metal blank. Even when the cutter is right, the slowest part of the job becomes changing it. This HCW1 horizontal boring mill solves that with a robot. A Keika arm pulls tool heads off the spindle, parks them in a carousel rack, picks the next one, and slots it in automatically. The HKOTA HCW4 horizontal boring mill comes together. A 53-tone base block lowered into position. Some heads aren't just cutters. They're entire 2-axis milling assemblies that bolt onto a larger main machine. The UFK 1000 is one of those. Tested at 700 revolutions per minute, 4 mm cut depth, 15.5 kilowatts power draw, finishing a spherical surface. At a certain scale, a machine isn't named for what it does. It's named for where the actual work itself happens. The SR4000 is a special multifunctional workplace built for very large shafts. The workpiece sets between centers on roller supports, indicator checked for runout in single microns, then turned and milled in continuous sequence. The spec sheet alone is enough to stop a normal conversation in the room dead cold today. Working area, 4 meters by 3 meters by 1.2 meters. Table, 5 meters by 5 meters. Turning speed up to 4,000 revolutions per minute. Control, Siemens. Spindle power, 100 kilowatts. Maximum torque at the spindle, 14,349 newton meters. Spindle diameter, 200 millimeters. Cartridge cross-section, 460 by 520 millimeters. Drill spindle inner taper is ISO 60. This is what gets ordered when nothing smaller can possibly take the actual cut. Buying one of these machines isn't where the cost ends. Getting it physically installed is a project all on its own. A time-lapse from a heavy, boring mill install shows what it takes. Foundation blocks come in first by forklift, surveyed and lined up against floor reference marks. The concrete bed has to be true to the millimeter over the full length, or every misalignment downstream gets baked in for the life of the machine. Get the foundation wrong, and no CNC correction will fix the part later on. Heavy guideway sections drop into place by overhead crane. Engineers torque each bolt in sequence so the bed doesn't preload into a curve. The column goes up next, the vertical structure that carries the cutting head. Cable runs, hydraulic lines, lubrication circuits, and chip evacuation get routed through dedicated channels. The boring head lands on the column under careful alignment, verified by precision measurement before any test cuts. Protective shielding, cable carriers, and the operator cabin go in last. A no-load run confirms every axis moves clean before the machine sees its first chip. At a certain point, you stop trying to move the work to the machine. You start designing machines that do all the work in one place. If the last act introduced the principle, this is the machine that puts it into practice. The SMT series horizontal multitask lathe handles 4 meters between centers and up to 2 meter maximum diameter on a single bed. The tool head travels in X, Y, and Z. Tool changers swap automatically. The setup runs so the workpiece never leaves the chuck until it's finished. Watch one full machining cycle end to end, and the time savings become obvious. Crane drops the rough shaft in. Hydraulic chuck clamps tight. Tools step through roughing, semi-finishing, and finishing in turn. A KKR arm handles tool transfers. A measurement probe with a ruby tip checks the finished part. Nothing leaves the chuck. No refixture errors enter the equation. The company behind this design has been building heavy machine tools for well over a full century. Energy, shipbuilding, mining, transport. One setup machining isn't only for shafts. This Italian-built custom center handles cast valve bodies and pump housings. A pallet swap brings the part in. Internal milling, external face cuts, drilling, automatic tool changes, all in one pass. The next twist, what happens when even the lathe shape itself changes? The lathe shape changes completely when you stand it up vertically. A vertical turning lathe VTL is the obvious choice when the part is wide and heavy. Gravity does the holding work for you here. Add a C-axis head, and the machine stops being just a lathe. The head can mill along the workpiece diameter, drill into the face, and contour pockets, all on the same setup that did the turning step. Same workpiece, no refixture, no transport across the shop floor. High output, high rigidity, the stability needed when the cut goes deep. Internal splines used to mean a dedicated broaching machine. With a milling head dropped through the VTL spindle, the spline gets cut straight inside the bore on the same machine. A motor housing looks simple and isn't. Round main body, terminal box on the side, mounting feet on the bottom, threaded holes spread across multiple planes. The old way, a lathe, then a mill, then a drill press, with 3 fixtures and 3 datum errors. The new way, a 1,600mm VTL with a live spindle and C-axis head, does the whole job. The table indexes the housing to each feature in turn. Drilling, reaming, milling, tapping, all done before anything leaves the chuck. Sometimes the cut needs an angle you can't get from a straight tool path. A B-axis turning head solves it. The head tilts to bring a long blade tool down into a small bore. Large diameter internal turning becomes possible where conventional geometry would bottom out against the wall. Mechanical clamps work, but they distort the part underneath. A magnetic chuck holds from below. No jaw pressure, no edge deformation, no localized stress concentration. The 2-mature magnetic table on this Toshilen VTL holds for turning, drilling, and milling in sequence. More usable tool clearance too. The C-axis idea works the same way on a vertical boring mill, only the orientation changes. The head moves to the side of the workpiece, drills laterally into pre-located holes, then sweeps milling cuts across cylindrical bores. The workpiece never has to be unclamped to rotate to a new face. Available across TOS, HULIN, TOS, KGRIM, and CKD, BLAN, SKO machines. Cutting and turning still leave the surface much rougher than a bearing actually wants. A 50 horsepower grinding head attached to the VTL brings the finish down to bearing spec. Auto Dresser keeps the wheel true, 4,500 revolutions per minute, mounted on the same machine that turned the part. A test part is how a new VTL proves it can really deliver what the spec sheet promised. First pass, chamfer turning on the outer edge of the part. Second pass, straight outer diameter turning to size. Third pass, end face slot milling using an end mill on the live spindle. The table indexes, the end mill plunges, the slot lands true. Every operation back to back, no break in the setup, no second machine pulled in. One ram is the standard. 2 rams cut cycle time roughly in half on the right job. A 4-metra VTL with dual rams attacks the workpiece from 2 sides at once. Even a stock floor basic turn has serious numbers. 78-inch table, 44, 0 pound capacity, 37 HP live spindle. The Fanuc CNC runs the full turn mill drill cycle inside one enclosure. But machining is only half the problem. Getting the finished piece out of the factory is the harder one. A finished turbine has to reach the power plant. It moves by multi-axle modular trailer with pilot escorts, oversized load placards, through rain and roundabouts. Now reverse it. Where do the cutting machines actually come from? Some companies don't build the parts. They build the machines that build the parts. A company like Waldrich Segan sits at the top of the supply pyramid. Heavy-duty milling, turning, grinding, texturing, and boring machines. The equipment that foundries and forging houses then use to cut giant castings into finished components. The downstream customers don't exist without it. Watching one of these heavy milling machines work is its own lesson in scale. The work envelope is room-sized. The bed is massive cast iron or poured concrete, isolated from floor vibration. The traveling gantry crosses meters of X-axis travel without losing thermal stability. A critical detail, since the steel of the machine itself grows and shrinks with workshop temperature, and the control has to compensate in real time. Every micrometer of error in this machine becomes a micrometer of error in everything it ever cuts. A grinding head finishing a turbine rotor surface, a texturing head laying a roughness pattern on a printing roll, a boring head opening a cylinder bore. Each operation depends on the machine's geometry being true. Automatic tool changers cut idle time between cuts. Multi-spindle configurations chew through different operations without a reposition. Probe systems verify each finished feature before the next one starts. The operator watches from a CNC console, not chasing the part around the shop with a tape. The downstream effect lands everywhere. Reliable energy generation depends on machine tools like this. Shipbuilding depends on it. Mining equipment depends on it. The German Waldrich House has been at this trade since 1920 itself. Engineering and production cover everything from small subcomponents up to the massive structural parts that go straight into the company's own machines built. They machine their own large parts on their own machines. A closed loop few competitors anywhere actually match. The customer base ranges across diesel engines, turbines, generators, ship propellers, tool and printing presses, and rolling mill components. Automation packages include tool exchangers, spindle unit changers, and workpiece changers in flexible production cells. Service-based coverage runs across Europe, North America, and the Far East, with remote diagnostics and spare parts available for machines on shop floors for decades. Want to see what one of these machines does once it lands in a customer's plant? A large marine-class diesel engine block sits inside a Waldrich enclosure. Probes measure the part first, then milling, drilling, deep boring through the bore axis. Tool magazine swaps automatically between operations. Coolant runs continuous. Not every machine builder is purely cutting. Some are assembling complete machines downstream of the cutting stage. A 6-crank process gas compressor moves from 3D CAD design straight through high-precision machining of cylinder housings and crossheads into structural assembly where overhead cranes lower the crankshaft into the main body of the machine. Hydraulic fasteners get torqued in proper sequence. Pressure tests run for hours. The whole compressor gets crated for sea freight, sometimes destined for Houston Port. What begins as a rough casting weighing tens or even hundreds of tons ends as a precision component measured in fractions of a millimeter. Every machining pass removes material, but it also reveals the planning, skill, and engineering hidden inside the metal. As machines continue to grow in size and capability, one question remains. How much larger can these castings become before manufacturing reaches a practical limit? And if a single component can already weigh more than a house, what industries will demand the next generation of giants? Let us know which machining process impressed you most and which factory-scale operation you would like to see explored next. Thanks for watching. The world is full of machines most people never get to see up close. We'll bring you the next one. So subscribe before you head out. Until next time, take care.